Thanks very much for everyone. And today I will give us a talk on global U-Lights and local U-Lights of function fields. Yesterday I have gave a talk in a workshop on the genus fields of Artin-Schwer extensions. And today I will give the talk is another subject. Now we will begin this talk. Let K be any Galois extension of Q. UK be the unit group of K. For any place V of K, let UV be the group of local U-Lights of KV. Recently, Li Yan and Professor Zhang Xianke considered the following problem: whether there exists an old prime P such that the map and the following map is injective. This means that this is a number field, and K is an Galois extension of Q, and there is a and we consider the UK. UK is the unit group of K, of OK, and for a prime P, for old prime P, and there is some prime lies above it. Suppose there is G prime lies above it. Now there is homomorphism, natural homomorphism from this group and from the left group to the right, UK square to this. And there is a there is a natural homomorphism from this group to this, because if a unit is in the globe is a global square, then this unit is of course a local square. But the problem is that if the unit is a local square for P1 to PG. Is this unit a global square? This is a problem. And as pointed out, their paper has been published in Journal of Number Theory. And as pointed out by the referee of the Journal of Number Theory, this problem in some special cases has been considered by Kummer, Hassai, and Foliage. And they do not give a complete solution of this problem. In 2007, Li and Professor Zhang Xianke has gave a complete solution of this problem. In fact, they proved that there exist such primes, whether there exists this prime such that the prime lies above this is injective. They proved there exists such primes is equivalent to this group. This module is a secanic Galois module. Is a secanic Galois module. And as an application, they gave an application. And they also proved that if the class number of the second atomic number fields with conductor a power of a prime, then such prime exists for both the maxima and maxima real subfield of this second atomic number field and this second atomic number field. And if the class number of this the maxima real second atomic number field is odd, and according to the referee of the Journal of Number Theory, he called this is the analytic proof. Of an open problem. and they gave a condition for the parameter, not restrict and not so restrict and the parameter as the previous works. And so he called this is the analytic proof of an open problem. Now we can Q, the integer in Q is Z, and we know the unit group of Z contains only 2 elements. But we know if we consider the function field situation, this group and the unit group of this, and the analogies is very low. The unit group contains this and contains the is bigger than this unit group is bigger than this unit group. So I think in function field this will has a more general result, and this is indeed the case. So let K be a geometric Galois extension of the rational function field. And geometric means that this extension contains no and constant field extension. Let OK be the integer closure of FQT in K. Let UK be the group of units of OK, and UA be the group of local units of KV. We generalize D and Zhang's method to consider the following problem: whether there exists a finite place P of FQT such that the map is injective, where D is a factor of Q minus 1. And we generalize their method to consider this problem for function fields. And D has gave a talk on his proof in a seminar in Tsinghua University, and I discuss this problem in function field with him, and we can solve this problem for function field. Let mu D be the group of these roots of unity. We will prove there exists such places P if and only if this group is a cyclic G module. And we also want to give 2 applications. And it is well known that there are 2 function fields are very important. The one is the quadratical function field. The other one is the cyclotomic function field. Now, if when K is a quadratical function field, we will prove in section 4 that there exists such places if and only if K. The first case is K is imaginary. The second case is K is 0 and D is odd. The third case is K is real, D is even, and there exists a fundamental unit epsilon 0 of OK such that n epsilon 0 is a generator of FQ star. It is well known n epsilon 0 has 2 cases. One case is that it is a generator of FQ star. Now, this page is a cyclotomic function field case. Let A be a monodic irreducible polynomial. Suppose K is the 8th cyclotomic function field, and K positive is the maximal real subfield of K. In section 5, we will prove that in such places exist for K and K positive if the class number of K positive is relatively prime to D. And it should be noted that this proof heavily relies on the Glavich and Rosen's work on synod secular units in cyclotomic function fields. Now we will begin our proof. And for begin this, and in our notation, K will be a rational function field, and K is a geometric Galois extension of this field. And we consider this problem not only use K and use another field K and use this field. And this field is bigger than T, than K, and we want to use this field to get our result. Now, since FQ contains this root of unity, L is an abelian extension of K of exponent D, denotes the Galois LK is H. And the Galois group of LK is H. And the Galois group below K over FQT is G. Now we can define an action of G on H, an action of G on H as follows. Conjugate action. And G belongs to G, and H in H we define an action. And should be noted that G is in this Galois group, and this is a normal extension, so we can extend the action of the Galois group to LK, and we can extend our action to the LFK, LK over LK. Now, by Kummer theory, reference 5 is Serge-Lang's book, Algebra. And by this book, he introduced to us about the abelian Kummer theory. From the abelian Kummer theory, there is a Lagrangian degenerated G-equivalent bilinear pairing from H and UK modular UK this power to mu D as follows. So H isomorphic this home group as G modules. The action of G on home group is defined as follows. Where we learn the home group can be written as Fu bar. So G acts as F. We let G inverse multiplicative U bar, and we let F act on it. So this defines the action of G on the home group. And under this action, the home group become a G module. So from the Kummer theory, we can have this isomorphic of G modules. Assume that the infinite place of FQT split into R places of K. By Dirichlet unit theory, the rank of UK modulo UK's disk power as Z modulo DZ module is equal to R. And from Dirichlet's the unit theory, the free part is R minus 1, and there is a torsion part, and we will modulo its disk power. So we can give this result as a ZDZ module equal to R. Also, there is a linear independent ZDZ modular DZ basis of UK modular UKD as U1 to UR. Then it is easy to show that this group H can be decomposed as the following, the direct product as the following Galois group. The isomorphism is given by restrictions. The following is a Chebotarev density theory for global function fields. Let LK be a Galois extension of global function field, and the Galois group is this. It should be noted that in the general statement of Chebotarev and the density theory, we don't assume this Galois extension is abelian. So let's say conclude in H be the conjugate class, and SK be the set of premises of K which are unramified in L. So we have this Dirichlet density. We can compute this Dirichlet density, and this is very important theory and in number fields. So under this Chebotarev theory in function field case can be proved in two ways. One is by adding L function, and this proof sketched in Zosen's book, the reference 7. The other proof has given by 1983 and in this journal. German journal. In this journal, the elementary proof not use the adding L function also can compute this Dirichlet density. So we can say this is also an analytic proof. Begin to prove our main result. We did a lemma that U in UK and P be a place of K which is unramified in L, then U in UP the this power if and only if the adding symbol over P on P fixes and this field and the proof is very simple. Very simple. Only some few words. If U in UP's this power, then we have P split completely in this field. This is very simple because KP, if U in UP this power, KP, this field equals to this. So we have E, the ramification index and the residue class degree are all equal to 1. Since P is unramified in K in this field, from the property, well-known property of the adding symbol, we can conclude that this adding map is trivial, as the adding map simple satisfies the restriction conditions, so we have our result. Now we prove the main result. Before this proof, we gave a remark. This remark not be used in our proof. But this remark is also very interesting. The natural map is this map, and it should be noted that this time we run over all finite places of K, but in our question we only let the primary places runs over one places, runs over. But this situation we let the way runs over all finite places of K. This question naturally arises from our question. But it is surprised. This question is very easy to answer. That U belongs to the kernel of the map. Then U in U with this power for always by lemma 2. And this adding symbol is identical for all finite places of A. And because the infinite places are finite, so the Dirichlet density is equal to 1 by Chebotarev. The density theory, this extension is trivial. So U in UK's this power, we can say from the this theory, and this if this is identity to 1, and this is only one element, and this is one element. If this is identity to 1, then this group is a trivial group. So we can use this Dirichlet and the Chebotarev, the density theory, to prove this. Now, before the proof, we need another lemma. This lemma is very important. Let P be a finite place of FQT, then the natural map is injective if and only if there exists a place where divide P. Hence, for one way divide P, and this is definition of the action of the G module under the property of the adding symbol. We can say this is this can be established for one way divide P such that the adding symbol on way is ZD is a G modular generator of H. Is a G modular generator of H. H is this Galois group. Now, proof of this lemma. And let U be any unit of K by lemma 2, and we have this if and only if conditions. If and only if. This is from lemma 2, and it is obviously that if U in UK's this power, this extension is trivial. We can say it easily. So by substitution, by substitution the conditions in the first equation, we can say this map is injective is equivalent to the following condition, under the following condition. So we have from the Galois theory, this is equivalent to the subgroup generated by VLK for all V divided P is equal to H. And this place, as pointed by the referee of arithmetic, he pointed out, and this we can conclude this not only use Galois theory, but also use the abelian-Kummer theory. In number field, if we can use, if someone can in number field, the extension you can use the extension of you can use the structure of the relative extension of the quadratic field is okay. But in function field, it is must use the abelian-Kummer theory in Sergeant's book. One of the abelian-Kummer theory is in Sergeant's book, and that abelian is well known. That is the B, you use Sergeant's notation, the B to Kp gave a bijection from the subgroup of K K star contains K star's this power to the abelian extension K of exponent and quotient M. And this and this is very important and pointed out by the referee. And recall the definition of G acting on H in section 2, and the first equality is from the property of the adding symbol, and the second from the definition of the G module act on H, the definition of H as a G module. So from this we can say this is also equivalent to VLK. VLK is a G module generator of H for any V divided P. Now we can prove our theory. There exists a final place P of FQT such that the natural map is injective if and only if the home group is a cyclic ZD-ZG module. Since H is isomorphic to the home group as a ZD-ZG module, the only if part follows easily from lemma 3, easily from this lemma, easily from this. Because there is an isomorphism from the home group to the Galois group. H is a Galois group. H is a Galois group. And from the abelian-Kummer theory, we have an isomorphic of these two G modules. So the only if part is very easy. Conversely, if H is a cyclic module, and let sigma in H be a G module generator of G by Chebotarev density theory, there exists a final place P such that PLK equals sigma. Of course, there is an infinite. We only use one. So as also by lemma 3 and the condition is find a P such that PLK equal to sigma. So this satisfies the condition of lemma 3. So we get that this from lemma 3 we get that this map is injective. And this is lemma 3. We find a generator. Now, but we say from this theory cannot be used very freely because there is a home. And the home, if this home can be deleted, there is as a G module, cyclic G module, and requires this module as a cyclic G module. But we want to get that if whether this group is a cyclic G module. This group is a cyclic G module, but we want to get this group is this group a cyclic G module? Is this group as a G module a cyclic G module? Can we translate this condition to this? This is a problem. If we can translate to this, we can use this theory very freely. So the following is to try to translation to this. And the following definition can be found in page 371 page of Rosen's paper. Rosen's paper we also used in yesterday's talk, and the Hilbert class field of function field. The Hilbert class field of function field. This is a very important paper. In this paper, and he gave a definition. An extension k of small k is called totally real if the primary and infinity, which crowns infinity of k. K is a rational function field, split completely in k. Now, this lemma, this is a lemma. Let G be a finite group and V be a free ZDZG module of rank R. Assume G acts on V linearly, then V is a cyclic ZDZG module if and only if V star is a cyclic ZDZG module also. So, from this we can say that we can delete the home and get this and get this. In the original manuscript, we gave a proof of this lemma, but by the suggestion of the referee, he said this proof is not needed in this paper, so we deleted this proof. He said this is very easy, can be very easy to prove. Now we can give another result. That K is a totally real geometric Galois extension of FQT. There exists a finite place P of FQT such that the natural map is injective if and only if this group is as a G module. This group as a G module is a cyclic Galois module. And this proof is also very simple. And suppose this suppose the extension is n. By definition, K has n infinite places. By Dirichlet's Euler theory, UK module, UK's disk power is a free ZDZG module of rank n. In this case, we have explanation of this in the blackboard. By theory 4, the map is injective, is equivalent to the home group is a cyclic module. Using the lemma 2, from this we get the desired result. The lemma 6 is this, using this, and the theory is this. The previous theory is this. Using this theory and the combination from this lemma and the combination from this condition, we can delete the home symbol and get a cyclic Galois group. But we think this cannot also be used very freely in some cases. So we get another result. A unit U is called a Minkowski unit if its Galois conjugate generates a subgroup or finite index in the whole unit group. We know such unit always exists, and this line is Washington, L.C. Washington's famous book, Second Introduction to Cyclotomic Fields. And his proof is for number fields, and we can check easily his proof is also okay for global function fields. Now we can get this result, that K over FQT be a totally real geometric Galois extension. There exists a finite place P of FQT such that the natural map is injective if and only if there exists a Minkowski unit epsilon such that the index of this group in UK is related primarily to G, to D. And this proof is also very simple, only few sentences. By theory 4, the extension distance of such P is equivalent to this is a cyclic G module. This means there exists a unit epsilon such that we can get this equality. And let E equal to ZG epsilon, we get the following equality. UK equals this. And this is Euler substitution, and the modulo E in this equality. And from the property of the finite group, we can say this. the important case, I think the very important situation is the task. The very important task is to give some of the applications of this result. Some of the applications of the result to answer many problems. To answer this problem for many fields, each for both for number fields and global function field, we need to answer this problem. We answer this problem for two important fields. One is called radical extension of K, but in this case we not assume. We assume the characteristic parameter 2. This is different from the talk I have given yesterday. Yesterday I have gave a talk on artificial attention in the workshop, and in that case we assume that 2 is equal to the extension degree. And this case, but in this paper we do not assume this. We will use developed in section 3 to investigate. We gave application of this to theoretical function fields. And such field can be written as K squared D, where D is a square-free polynomial of FQT. And this field had been systematically studied by E. Ardin in his PhD thesis. You can see this Ardin's paper in Ardin's classical collected papers of Ardin. You can see this in this book. This is the first two papers of Ardin, and these are all given by Ardin. Fix a generator G of FQ star, then we can assume the leading coefficient of D is 1 or G. The infinite place in rational function field, the infinite place in this, speeding, inertia or ramified in K respectively. When the degree of D is given, the signature of D is equal to 1, the degree of D is given, and the signature of D is equal to G, or the degree of D is odd respectively. And then the field is called real, inertial imaginary, or ramified imaginary respectively according to E. Ardin. When K is real, we let epsilon 0 be the fundamental unit of K. Any fundamental unit is determined only up to multiplication by a constant. Thus, its norm is either a square or G times a square. So by multiplication epsilon 0 by an appropriate constant, we can assume an epsilon 0 is 1 or G. And recall my talk yesterday. We can say there is somewhat analogous for Ardin Schiller extension under this situation. The Ardin Schiller extension is also classified as 3 cases according to the behavior of the infinite places of FQT in K. And this is also okay for Kummer extension. This is a Kummer extension, special case of a Kummer extension. And in Ardin's paper, he does only give this. He gave the other arithmetic of the quadratic function field following the classical study of the quadratic number fields. Now we can give the our application of this. There is a finite place of P of FQT such that the map is injective. If and only if K is imaginary or K is real, 3 cases, one is K is imaginary, one is K is real, and D is odd. The third is K is real, D is even, and n epsilon 0 is equal to G. D is this D. We consider D, and the epsilon 0 is a unit of fundamental unit of a quadratic function field, and this situation also classified for 3 cases. Now we can prove of our above theory. And if K is imaginary, this is very simple because UK from the theoretical United series, UK equal to FQ star and UK modular UK's disk power equals FQ star modular FQ star's disk power. And this is a secanic group. This is very easy to say. This is a secanic group. Thus, this G module is a secanic G module. By theory 4, there is a finite place P of FQT such that this is injective. Now, and the real case is more complex. The case from the decomposition of the unit group by coronary line, the extension of such places is equal to the extension of a Minkowski unit epsilon, such that they satisfy this condition. And if K is real, of course it is totally real because this is a quadratic extension. So we classify to two cases. If n epsilon 0 equal to G, we can take epsilon equal to epsilon 0, then UK equal to that Galois module. Because n epsilon 0 equal to G, we can product all of this group, FQ star. So, if n epsilon 0 equal to 1 and D is odd, we can take epsilon equal to G epsilon 0. Then this Galois module can be decomposed by two parts. This is easy to say. This Galois group can be decomposed by two parts. One part is Z epsilon, two part is generated by n epsilon. So from the definition, from this equation, we can say the last equality. So thus we have UK modular ZG epsilon equals to 2. So this is primary 2D. And if n epsilon 0 equals to 1, because we assume D is odd, so this is primary 2D. And if n epsilon 0 is 1 and D is even, for any Minkowski unit epsilon, we can write this decomposition. As above, the G epsilon can be decomposed to two parts, and this group contained in this. So we can say to divide this, and D is given, so to divide this, and so this proof is complete. So this situation not satisfy this condition. So our proof is finished. Now we see the second atomic function field case. And before starting the main theory of this section, we introduced some notations. And let K equals FQT be a rational function field, and R be its integer, the polynomial ring. Let K be the KSA, be the algebraic carrier of K, in order to construct the class field of the explicit class field of K. Correlate introduces the R module structure on KSA called the correlate module. And the correlate module is well known. It is a special case of Green field module. It has rank 1 Green field module over the rational function field. It's rank 1 Green field module. So this is a ring homomorphism divided by this. This is also well known. On this page, all of these are well known. And the alpha, the action on KSA is defined as follows, those action. So we can get the torsion part, and the other two torsion part to K, we get a second atomic function field. From the chapters 12 of Rosen's book gave us a nice exposition to the theory of second atomic function fields. Let S infinite be the set of infinite places of K lambda m, and UN be the group of SF infinity K lambda m unit of K lambda m. And this is some notations. And for simplicity, let P3 denotes the following property. There is a finite place P in FQT such that, and this property is the question we ask in introduction, and so we in this section we must form second atomic function field to get an answer to this question. Now we get an answer to this question like this. Let A be a monadic irreducible polynomial in FQT. Let K equals to K lambda A and K primitive be the maximal real subfield of K. And let HA be the class number of HOK. Let HA primitive be the class number of OK primitive. If D divide Q minus 1 and HA primitive relatively primary to D, then this property is there exists a file, whether there exists a file place such that the map, the homomorphism is injective and is holds for both K and K positive. And before the proof of the above theory, we briefly recall the Galovic and Zossen's work on synodal secanic unit in second atomic function fields. And this can be found in the paper, Zossen's paper on the second atomic unit. Let M be a monadic polynomial in FQT. Let lambda be a primitive M torsion point. Define this set S. And we can say the element as defined by Zossen, the element in the subgroup generated by S is called the Kummer-Hilbert secular units, denoted by this. Let G be a multiplicative subgroup of K lambda M, and the not equal lambda M, K lambda M, and which is generated by FQ star and lambda M star, and denoted 0. The element of C and C positive divided as follows are called the C0 second unit of K lambda M at the K lambda M positive. This definition is in Zossen, Galovic, and Zossen's famous paper on second secular unit of function field. Remark: since A is irreducible, from 3 we know from Galovic and Zossen's paper we know this equality: UK equals to UK positive, C equals to C positive, and C positive can be written as follows. In this case, A is irreducible. In the case A is irreducible, Galovic and Zossen proved that this classical result due to Kummer. This the classical result of this situation of number fields due to Kummer. This is the function fields due to Galovic and Zossen. Now, using this theory, we can prove our theory for second atomic function field. And we must, before the proof, we must point out this proof belongs to the referee of Actam Arithmetic. And the original proof of my original proof is very long and contains a gap. And thanks to the referee, he gave a simple proof and filled the gap. Let G equals to this Galois group, this Galois group K, and the K positive is the maximal unramified subfields of K. Now, from the above remark. From this remark, we can say this: UK equals UK positive. From the above remark, we have this equality. Thus, the home is a secanic ZDZG module if and only if home is the home for this. For the right is also secanic, because this is the same group. By theory 4, P3 holds for K if and only if P3 holds for K positive. Why should we do this? Because we must get a field which is totally real. So we can use one of our theory, one of our result. We must get a field which is totally positive. And if we use this field, this is not this is not totally positive, so we cannot use our theory. But if we use this field, we can use one of our theory. By theory 4, P3 holds for K if and only if P3 holds for K positive. Because this is because from the previous sentence, the home is a secanic G module if and only if the other is a secanic G module. by series 4, P3 holds for K, if and only if P3 holds for K primitive from the above series 13, and the Galovic and Zosins and theory, well-known theory, and we have this equality. So, from by our condition is this. Our condition is this. To be noted that this. From our condition, we can say under this equality, we can say this is relativity. If we can show that the C primitive is a secanic ZD, secanic G module, then by correlation line, we will complete the proof. Suppose M is a generator of this multiplicative group, FQT modulo A, FQT modulo this ideal, the multiplicative of this. Since by the above remark, C primitive equals to this, and the C primitive is generated by this is from the definition of the Zosen and Galovic and Zosen. So for each polynomial W relative prime 2A, there is a unique element sigma W in G such that this equality holds, where lambda is a primitive A torsion points. Using the definition of the group action, the multiplicity of sigma n and the cancellations in the telescoping product, we have this. Thus, C primitive equally to this equality and is a secanic model, and this proof is finished. And thanks to the referee, we can say this proof is very simple. We get a very simple proof of the second atomic function fields. And after we see the references I will also remark some of the recent work of this direction. Some of the recent work. First, we see the references. One is Artin's PhD thesis on the quadratical function field. The second is Carlet's Rowland paper on the second atomic function fields. And the third is Zosen's and Galovic and Zosen's paper, unites and class groups in second atomic function field. And the fourth is Hayes' famous paper on the class field for rational function field. And this also has been generated by Junfield. And this is a book of search now. And the last is Li and Zhang's paper on global U-light square and local U-light square for number fields. And this already published in Journal of Number Theory. And we have another two work of Zosen. One is Zosen's book. The other is Zosen's the Hilbert class in function field. The last is book. And before the conclude this talk, I must introduce some of the recent work of us on this subject. This work is finished on the beginning of the last year, but from 2008 and to this year and to today, we will still consider this problem because we know there are many problems still unsolved. For example, both for number field situation, for function field situation, and let's say the number field situation. For the number field situation, we can say in Li and Zhang's paper, they assume such prime is odd. But if the prime is this, and how do we answer this question? How can we answer this question? Is this? And Li Yan has solved this problem in this year. In the April of this year, he has solved this problem. Completely solved this problem. And he said there is only one cases, except only one cases, this map cannot be injective. This map cannot be injective, except only one cases. And we do further works on this, and for function, both for function field and for both for function field and for number fields, we can say our result is an algebraic result. There is a such placed P if and only if the whole group is a secanic G module. This is a purely algebraic statement. But in the proof, we use the following. We use this important theory. This theory, the Chebotarev density theory. This density theory is an analytic theory. Now a problem arises: how to give a purely algebraic proof of our result? How to give a purely algebraic proof of this result? And there is a book. There is a nice book on this subject. There is a nice book in a series, lecture notes in mathematics, published by Springer. One of this book, and this book gave a connection between the Chebotarev density theory and the class field theory. So, in 2000, in this month, I gave a purely algebraic proof using cohomological method in this month for number fields. But he found this proof has a gap, contains a gap, a large gap. And he said a large because there is a 2 and there is some and there is many premises about 2. And in number field cannot solve this. But in function fields, and there is not a primary. We do not consider this situation. We do not need to consider this situation. So, but this proof given this month cannot also cannot be applied to function field. So after this, I gave another method by modification of my method given in this month, and gave a purely algebraic proof by cohomological method. And this is in this month we have get a for function field. And still, we cannot give a proof for purely algebraic proof for the number field case. This is still a question. And the other question is this, and some applications is also very important. Some applications, one applications is two cases, quadratic function field, and but there are many cases. For example, in this second atomic function field, we use the C0, the second atomic units. But it is well known that Professor Yinlinsen has generated this second atomic unit to generate global function fields. Can we use his definition of the second atomic secular units for general global function field to give an answer to this problem to the general global function field? Also, Professor Fenke Qin in 1980s gave another definition of C0 second unit for abelian function field. Abelian function field is defined as a subfield of the second atomic function field. Is defined as a subfield or any subfield of this field. And Professor Fenke Qin generalized this. So can we answer this to the subfield of the second atomic fields? And this is also under this also problem we can consideration, and this problem can also be consideration for number field case. And another result point is suitable point is the quadratic function field case. Quadratic function field, this case, and how to can determine n epsilon 0 is equal to 1 or g was given by a paper by Ji Chun-Gang published in Journal of Number Theory. So in quadratic function field, we usually solve this. And so we conclude this this talk. Thank you very much.
Question?